So binary operations are the most well studied, I think, of algebraic structures. Most of the arithmetic operations that you learn coming up through the grades, addition, subtraction, multiplication, division, exponentiation, those are all examples of binary operations. You have to give me two inputs and I give you a single output of the same type. Right? And so when I have a set and a binary operation on that set, together it forms an algebraic structure that is so important we give it a name. We call it a magma. Which is I don't know why they call it a magma, why it has anything to do with molten rock underneath the Earth's surface. I don't know if it has anything to do with it, but we call it a magma for whatever reason. So that's all a magma is. It's an algebraic structure with a single binary operation. So it doesn't give us a whole lot to work with, but it does give us a way of taking two of my elements and producing for you a third of those elements. Right? When I have a small set of elements to work with, one of the best ways of understanding the structure that's defined by a magma is by putting it in like a times table. These little times tables are things where if you've had an abstract algebra class, you probably use these for groups, for example. It's the same kind of idea where the way we construct one of these operation tables is that on the same row as an element x and the same column as an element y, we will place their product, the result of taking x and y and operating on them by my operation, right? So we find x operate y in the same row as x and in the same column as y. And I want to be very careful about distinguishing rows from columns because in general, that probably matters, right? We don't know for sure that, if x and y are flip-flopped here, that x operate y is not necessarily the same thing as y operate x, right? All we have in a magma is the ability to take two elements and produce for you a third. We don't know that it has any other fun properties that we might want it to have. We're going to get there. So what I want us to get comfortable doing is thinking about how an operation table can tell us about the structure of a magma, right? How do we work our way around a sort of a times table in a situation where it's not necessarily numbers and it's not necessarily timesing, but it is telling us about the structure, the algebraic structure of a magma. So in this next activity, suppose that we have as our set just two elements, one of them called positive, the other one called negative, and here is an operation table on a magma defined on that set. Right? So positive operate positive gives me positive. Positive operate negative gives me negative, and so forth. So my first question is, what do you think the operation of this magma is? I'll have you do this in your teams. And then I want you to push the envelope a little bit. Write a different operation table for a magma on the set even odd. So it's now different elements in my magma, but it still has just two elements. Write an operation table that looks exactly the same in some way as the one that we start with. And then do it again, but write an operation table for the same set, but one that looks different from the example above. Right? Does everybody understand kind of what I'm asking there enough for us to get into our rooms and try it? So what I like about this activity, I think, is that it sort of honors the little shorthand that we come up with our students up through the early grades. Things like, oh, even times even is even, or positive times negative is negative, right? Those little shorthand things. What we're really doing when we're communicating that is we're really talking about a particular algebraic structure. We're communicating about a magma. In particular, the magma that's up here, right, is the magma that tells me the multiplication rules, the sign rules for multiplying two numbers, whether they're integers or rational numbers or real numbers, right? That positive times positive is going to give me positive. Negative times negative is going to give me positive, and so forth, right? So that is just a communication of an algebraic structure right there. It's a magma with two elements in it. And it's a magma just because the result of operating on any two of those elements is another one of those elements, right? Positive times positive and positive times negative, and all those are going to give me an answer which is either positive or negative. And we can define another magma on the set of evens and odds by using the same rules for addition, right? And we end up with this magma, this operation table that looks exactly the same as the one that we had up here for multiplication for positives and negatives, right? So from an abstract algebraic standpoint, these two magmas, the one up there and the one down here, the magma for multiplication rules of integers and the magma for addition rules of even and odd numbers, those are the same structure, right? The only thing that's different are the names, right? The concrete sort of reality of them, but the underlying structure, those operation tables look identical to one another, right? Just in place of even, we've placed the word positive. In place of odd, we've placed the word negative, but all of that works exactly the same. So from an abstract algebra standpoint, we probably don't want to see the difference between those two. From a concrete arithmetic perspective, sure. I mean, we want to know what both of those are talking about, different things. But from the algebra perspective, it's sort of high-minded. No, those two are exactly the same. If we want something that's fundamentally different, because we're just defining a magma, sort of, all bets are off. We can do whatever we want to. So as long as we're filling in these cells with the word even or odd, right? We can fill them in any way that we want to in a magma, right? Because we have no rules that constrain us for how we do that. But if, for example, we choose multiplication of numbers and how that respects evenness and oddness, then we get a different kind of magma, right? Because even times anything is going to give me an even result. The only way to get an odd product is to multiply two odd numbers, right? So here is a set of multiplication rules for multiplying even and odd numbers that also forms a magma, right? But it forms a different magma. It's clearly sort of different than the one that's above it. There are sort of 3 ways to get an even answer in this magma. There's only 2 ways to get an even answer in this one. Right? If I'm adding, I can get an even number only by adding 2 evens or adding 2 odds. I have to add 2 numbers of the same parity to get an even answer. Where if I'm multiplying, I can do that in 3 different ways and get an even result. So that is fundamentally different, right? So each one of these is, you're really secretly communicating about a magma to students when you use those little shorthand sort of rules of thumb for arithmetic.